Alrighty, so this positive definite idea, um, again, it's a matrix thing. So I have this matrix A, and we define strictly positive definite as if I take X transpose times A times X, that's a scalar, that's a real number. And so that will always be greater than 0. Now, that's for any x not, any x not, where is my eraser? Right there. Any x not equal to the 0 vector. I had left that out of the statement. I had meant to go put that back and I forgot. So you've got that, and then so that's positive definite, and then positive semi-definite would be the case where you've got x could be equal to 0, so positive semi-definite. And but again, you see, so if we look at a 1-by-1 case, right, that it means that I would have like some x1. Now a 1-by-1 matrix would just be some letter A, and then times x1. And since x1 is a real number and so forth in this case, there is no real transpose. But when you run that together, you get a x1 squared. And in that, those two things are given to you, that the function x squared is positive. Well, is convex. And then a times x squared, as long as a is greater than 0, is also convex. And so convexity and positive definiteness are very, very related in that sense, in that that I also know if this is true, this is one of the things you prove, or you're asked to prove, that then it's, it's an, well, actually, now I got to remember, let me look here at, I've got it somewhere. You can't see me looking, but I'm looking. Let's see, so positive, yeah, so I had to do an if and only if. That was the number 8. And so it's only, though, about this quadratic form, and as far as the positive definiteness and positive semi-definiteness. Okay, because, for instance, if and we'll, for the moment, we'll keep it very simple with a 1-by-1 matrix. And so suppose I've got ax squared like this plus bx plus c, and I know that a is greater than 0. Okay, in that case, well, what I know is that this is convex. Okay, but to talk about this as positive semi-definite makes no sense whatsoever, or positive definite. It makes no sense whatsoever, because positive definite, positive semi-definite is about A. And since A is greater than 0, then what I can tell you is A is positive definite. And because pretty much that's going to be it for a 1 by 1 matrix. Now, if you go to a 2 by 2, all of a sudden, right, you got A, B, B, and C, because it has to be symmetric to talk about positive definiteness and positive semi-definite. Now, if you're working with this, you got an x1 and x2 here, and x1, x2 like that. Okay, and again, under the right conditions, what we're saying is, hey, if this matrix here, we'll call this A, if this matrix A is indeed positive semi-definite, that we're asking you to show that implies that A, oops, now I've got to, oh, come on, there we go. That the function then x transpose AX, which we see up here, if A is positive semi-definite, that implies this function will be convex. Okay. And then similarly, you want to show that if x transpose AX is convex, that implies A is positive semi-definite. Now, a shorthand notation for that is to write this, which again is a math idiom, because a matrix here, A, cannot be greater than or equal to 0, a scalar. Okay, it makes no sense. But the idiom is that under positive semi-definite, we know that this multiplication here will be greater than or equal to 0. But the reason you write it this way is that positive definite and positive semi-definite is a condition or a definition, a characteristic of the matrix A. It's not the characteristic of the multiplication. Whereas convexity is a characteristic of this function here. Okay, so they're very, very related, but they're kind of talking about slightly different aspects of the same stuff, and so you just have to be careful of that, and so in the end, you can, so suppose that this function is convex, so a x transpose AX is convex. Well, can you take convexity, properties about that we've already proved, to show that x transpose AX is greater than or equal to 0 for all x? Because that is then the definition of positive semi-definite. And so even though it uses that multiplication to get that condition, positive semi-definiteness is only about the matrix A. And so I think that's where you're kind of getting confused, is they have this sort of flip-flopped relationship. Okay, so with convexity, you're looking at this whole function, and you're saying it has a certain property, that property, if I call this F, then, we've got our F of Tx plus 1 minus Ty is less than or equal to Tf of x plus 1 minus Tf at y. So convexity is about the function, but it's interesting what we've been able to show is we can show convexity by knowing properties. Now, in particular, right, we were looking at the eigenvalues of A. Okay. And then, so you see the statement convexity is about properties of that multiplication, okay, but the way we show it, okay, the way we show it is through properties. In particular, we were using eigenvalues of A. Then, similarly, okay, if you have A is positive definite, or, well, we'll toss in semi-definite, then you see that's, you can, it's a property on this multiplication that defines our positive semi-definite, and so what you want to do is try to get at, now remembering that A is symmetric, you want to try to get at probably things about eigenvalues, okay, in order to relate these two ideas, right? So if I can say something, if I know something's convex, then I can say something about its eigenvalues. And if I can say something about its eigenvalues, maybe I can say something about this product. And vice versa, if I can say something about this product, maybe I can say something about the eigenvalues. And if I can say something about the eigenvalues, then I can say something about convexity. So that's this idea in 8. And I will say I have admittedly not been extremely straightforward and straight to the punch on all this because I don't want to do it for you. But I'm trying to get you to kind of see where maybe you are getting hung up on this idea. So hopefully this will help.